Let's consider the rational function f of x equals x minus 1 times x squared minus 1. If we want to figure out where the vertical asymptotes might be, we'll need to factor the denominator so that we can see where it's equal to 0. X squared minus 1 is the difference of squares. We know it can be factored as x plus 1 times x minus 1. But something interesting happens. We have a factor of x minus 1 in both the numerator and the denominator, and we can cancel those out. This leaves us with x plus 1 in the denominator and 1 in the numerator, because x minus 1 is the same as 1 times x minus 1. So we can rewrite this original function as a new function, 1 over x plus 1. And we can see here that we're going to have a vertical asymptote at x equals -1. So I'm going to draw a vertical dashed line to represent this asymptote. But instead of making tables of values to figure out what the graph's behavior is near the asymptote, we actually have another method that we can use, and that is transformations of functions. This function, 1 over x plus 1, is actually the original function 1 over x shifted to the left 1 unit. And we know that the function 1 over x approaches the asymptote on the top part on the right and on the bottom part on the left. So we can just shift the graph of y equals 1 over x to the left by 1 unit to see what this graph looks like, except there's one thing we have to be careful with. We know that the original function is undefined when x equals 1, because when we plug in 1 squared is 1, and 1 minus 1 is 0. We can also see that when we look at the factored form. When we substitute in 1 for x, we get a factor of 0 in the denominator. So this should not be defined when x equals 1. Well, what's going on here? If we look at Desmos to see what that graph looks like, we can see something interesting. If we look at this graph on Desmos and we hover our mouse over the point on the graph that would correspond to x equals 1, we end up with an open circle. And Desmos doesn't actually show you this unless you hover over that point. But what happens is this original function is not defined when x equals 1. So in the end, there's actually going to be a hole in the graph there, which we can denote by putting a little open circle there. So the reason we have a hole here instead of a vertical asymptote is because when we look at the function that we're given, we know that it's undefined at 1. Because we have a factor of x minus 1 in the denominator. So we cannot have the graph being defined there. But because this factor also exists in the numerator and we can cancel it out, this doesn't end up giving us an asymptote. It gives us something that you'll learn in calculus is called a removable discontinuity. And so it's just a little hole in the graph. In general, if our function is undefined at a certain number because of a factor in the denominator, and that factor is also in the numerator, if they could cancel out, then instead of getting a vertical asymptote there, we will just have a hole in the graph. Now, there's something very subtle that's going on here that I want us to be very careful with. And I want to explain what's going on. When we take a function or an expression and we simplify it, we take for granted that the simplified version is equal to the original version, when that's not always 100% true. In this case, the simplified version is equal to the original version almost everywhere, except when x equals 1, the original function is undefined when the new function is defined. So when we are simplifying functions by canceling something out in the top and bottom, we're not really changing the function for the most part. The simplified function is almost the same as the new function, but the thing that might change is the domain. We might have one number in the domain that's different between the original function and the simplified one, and what that'll correspond to is one point on the graph that's going to end up being different. So just be careful whenever you're simplifying a function, because the domain might change a little bit in the simplification process, and we always have to make sure we're using the domain of the original function. So in this case, we've got a hole in the graph at x equals 1.